webinar. My name is Bob Zavadil from Internex. I'm actually guest hosting for Charlie Smith, the Executive Director of UVIG, who couldn't be here today. Our topic this afternoon is behind-the-meter solar forecasting. And having been around for a while, I was musing before the call that 15 years ago, no one would really thought we'd actually be on this webinar this afternoon. Significant DER was not on anybody's radar back then. It was kind of far afield from the power system concerns we had at the time. Now, distributed energy resources, especially distributed photovoltaic systems, are a concern not just for distribution circuits, but actually at the bulk system level. And you can see that in terms of the RTOs and the energy markets, the activities that are underway to better understand this facet of renewables. At the same time, forecasting science has been advancing very rapidly over the last decade. There's been a lot of work in the foundational meteorology from federal and research agencies with regard to numerical weather prediction and those sorts of things. We have new technologies that are being brought to bear to assist with the weather forecasting as well as on the information technology side. And so I think today we're going to see or hear about a convergence of all of those things as it applies to forecasting of behind-the-meter photovoltaic generation. Our speaker today is John Dise, better known as Skip, I believe, who's the lead product manager from Clean Power Research. In his role as lead product manager, Skip works with solar developers, utilities, and energy agencies to design and integrate software tools into their planning and operating processes. He's also responsible for submitting R&D grants with the goal of building in new features that will allow for more accurate and automated intelligence around PV to grid integration. Skip has a BS in chemical engineering from MIT and an MS in mechanical engineering from UC San Diego. So before I turn it over to Skip, just a note about logistics. We're going to let Skip go through his presentation, and then we'll open it up for questions. We're targeting about 1 hour for this webinar, but we can run a bit longer depending on the questions we receive. I think we have a 2-hour time slot banked into this WebEx. I would recommend that you use the WebEx communication features for forwarding questions. That'll make it a little bit easier to sort things out or order them at the end when we open it up. So with that, I'm going to turn it over to Skip.
Thank you very much, Bob. That's a great lead-in to the talk today. I've seen, as I'm sure many have on the webinar, a number of great presentations this year from the UVIG group at the forecasting workshop and in other webinars that focus on the research and science behind the solar forecast, how meteorology meets the energy space, and it just expands when you start to talk about applying that to the behind-the-meter PV systems that are on the grid. So my talk today will focus on the fundamentals of behind-the-meter PV forecasting. To do that, I'm going to follow this agenda. We're going to talk about the challenges that are created, this energy transformation that is expanding beyond PV to distributed energy resources. At Clean Power Research, we're focusing on a platform to help solve some of these problems. I'll talk about how that piece relates to and applies to the BTM case. We'll then, maybe I'm reversing the order a little bit, but I'm then going to start to talk about what it really is BTM forecasting and where can it apply. The traditional renewable generation from the transmission scale and what we call utility scale plants create different problems than the BTM solar. And so developing solutions and applying forecasting tools to those two different types of generating assets is a different equation. We'll talk about that. We'll focus on the use cases and then how to apply that forecasting technology from its fundamental sense to specific use cases. I'll then highlight a couple projects that we've been involved in through the CEC and DOE to apply what we've learned in building the system to help address the problems associated with behind-the-meter PV. So let's dive in. We'll talk about these challenges that can be created when you install a lot of generation behind the meter or on the distribution grid. Across the utility space, as I'm sure many are aware, we're seeing this shift or this energy transformation that's occurring. We see the causes of this transformation being related to really 4 key influencing forces. We'll start and we'll talk about the technology. Not even discussing PV here, the access to different customer-sided technologies that can impact the electric grid are continuing to expand. EV models in 2008, there was 1 EV model available in the US market, and now through May we've got 13 and more to come, both total EV as well as plug-in hybrid electric vehicle. The addition of smart thermostats, again, has followed a similar curve in terms of the availability of different models. And so back in 2011, we were limited in the number of smart thermostats that we could choose from, and now we've got quite a wide range of options to install at our home. There's a commercial aspect of this energy transformation that's occurring, and I think this is being recognized across the utility and power industry through this survey result, where there is a lot of change that's happening with technology advancing, costs reducing, and options expanding for the consumer. There's a cultural aspect to what we're seeing now. There's an awareness that these new technologies are created. Oftentimes it's because of the marketing that these technology companies produce. I think the Tesla Model 3 is a great example of that. I certainly want one. Then there's the environmental component to what we're seeing, and a recognition from local and state governments where they understand the value of promoting on alternative forms and renewable forms of generation. The way that this is manifesting on the grid, if we now go and focus specifically on PVs, is just a rapid growth. This is a curve that goes only through the end of 2015, so we've got to tack 2 more years on here. But this type of growth is representative of the state of California, but is beginning to be mirrored across the U.S. and across the globe. And that impact of that growth is oftentimes publicized through aspects at the transmission level. I think the most notable one that I still hear a lot about is the duck chart, this notion that the load curve is changing. And I think we're well into that new paradigm now, where the load curve is being significantly impacted by all of the distributed PV or BTM PV that is on the grid. But a focus of what I'm going to show here today is that these impacts of this dynamically growing capacity behind the meter, it expands well beyond just the transmission scale. It goes all the way down even to the individual building level, where forecasting and technology solutions can be applied. At Clean Power Research, we're focusing on developing some tools. I'll just briefly touch on what we have here, but then quickly move into why those tools are important from a forecasting perspective. The number one aspect, and California got ahead of this curve back through the CSI program, is through enumerating and identifying where these generators are and what installed capacity is. So that was done through the PowerClerk software. This is now being shifted from incentive processing over to interconnection processing, where incentives are starting to go away and have gone away in many parts of the country. It helps to capture that information. I'll talk more about that. We have a second tool here, WattPlan, that focuses on customer integration, helps utilities engage their customers around decision making. And then our SolarAnywhere tool, which I'm the product manager for, focuses on developing software solutions through forecasting technologies that can apply to a number of utility use cases. So let's jump right to the interconnection piece, or the data management piece of behind the meter forecasting, because that's really where it starts. You have to have a good system for understanding what's on the grid. And we do this through our PowerClerk tool. There are many utilities that use different systems. But what we found is that having a central workflow that standardizes how applicants interact with the utility, provide information to the utility, can really benefit a number of use cases downstream. Here I show 4. So there's one, starting on the left, there's the use of the information that's captured just in presenting the location and heat map on capacity of what is installed behind the meter. There's a step of understanding what the impact of interconnecting new systems is on the distribution grid. And then there's other, again, applications that really benefit from having this central place to look in understanding what and where PV is installed. Then we can add on an additional client, which really the forecasting tools are. We view our SolarAnywhere application as an add-on to the PowerClerk tool, because it really relies on that information and benefits from having this central database of understanding what's installed on the distribution grid. So now I'm going to start to talk about a bit, what do we define as the BTM system? Why do we need to forecast it, and where can those forecasts apply, and to what use cases? So to do that, I'm going to start by defining what we view as the single utility plant. This type of generation fits more with the way the utilities have traditionally set up their generation. They procure energy at the wholesale from large central generators, transmit down to the distribution grid, and then sell at retail to the retail customer. These generators we'll define a utility plant as something that's transmission tied, high voltage, and the budgets are large because the capacities are typically large for these types of plants. These are in the megawatt scale, oftentimes in the hundreds of megawatts. The market structure is beginning to move to a position where the revenue lost from imbalance justifies the cost of a plant level forecast, meaning we want to forecast what the power and energy output of an individual plant is at 50, 100 megawatts. The site has employees there. They're O&M of the systems, the maintenance of these systems, and the investment in keeping these systems operating at as close to 100% availability is very high. And during the financing and development process, the specifications of these plants is very well known. The engineering and the constructions are verified. There are a lot of processes that the industry has developed over the years to get a really high level of detail about these plants. But the application of forecast tends to focus on one aspect of these plants, and one that many in the UBIG community may be familiar with on the wind side, in that you're forecasting the plant output either in a day-ahead market or potentially in the real-time market as well to schedule your generators for the upcoming day. The value in having a good forecast here is to reduce the energy imbalance. So if we have a forecast in orange and our actual PV output is in yellow, there's a certain amount of energy here in the difference between these curves that ultimately needs to be made up. The economics around this can be pretty well defined based on the short-term cost of the energy makeup through or lost revenue due to reduced generation. And so when we look at the utility process or system that's impacted by utility PV, it's very focused. It's generation forecasting. We want to understand what our generators are doing so that we can properly balance the equation of supply and demand. Behind the meter PV, however, has a number of different characteristics. I'd say the only thing similar is that there's panels and inverters in my mind. So you've got now a much more distributed asset. That's obvious. But what comes along with that is a much lower budget from the owner. That owner may be the homeowner. It may be a third party. It may be a bank. But the budget in maintaining these systems isn't always there. The loss of a single site might be small, but large if you have widespread reductions in the availability on site. A big difference is that you don't typically have your employees on site, so you don't have people necessarily that are inherently invested in the performance of these systems. You have oftentimes homeowners or business owners who may not be trained or understand how to remedy underperformance. And as far as information capture on the development and financing, this can have a wide degree of detail that is ultimately either requested by the utility at interconnection or even captured by the installer. But now when we look at what impacts BTM PV can have on utility processes and systems, the use cases are multiple of what we see at versus the utility level. So you've got a lower degree of information capture, a lower focus on O&M or high availability of the systems, but yet a vastly expanded number of applications where these generators can impact the distribution grid. And now some of these use cases may not become evident until the penetration or the relative generation of the PV to load grows to a certain level. But as we established, this is happening in many places across the country. So now let's go back to our diagram here of that central piece of interconnection. Again, that definition of behind the meter solar and the explanation of use cases just increases the importance of understanding where these systems are and what makes up these systems. So I'm going to talk about now, what sorts of information do we need about these systems, ideally, if we were going to give them a forecast that we would call accurate. So each of these systems exists on a homeowner's rooftop or a business rooftop. Sometimes they're ground mount, but they're tied to the distribution grid. We want to know the location. We want to know the capacity, the orientation of the panels, and how those panels are wired to the inverter. And in this case, we're also capturing the installation date or the PTO date when it comes to interconnection. Having that information allows us to group the systems. So in this case, this is a single system on the peninsula in San Francisco, and that then makes up a larger fleet throughout the state of California. Let me give a little bit more detail on what a behind-the-meter PV system spec entails, because it's important, again, from the forecasting aspect of what we're trying to do to understand what's being installed. So we break that up into 4 different headings here. A rooftop system, we want to know the site, and that might start with the latitude and longitude, or it might just be the zip code. Again, we're dealing with a varied set and a non-standardized request when it comes to capturing this information. The orientation, so that can have a dramatic impact on how we predict the output of these systems in individual or in aggregate. And the tilt of the roof, both of those things determine how the system outputs power throughout the day. The hardware is important, specifically the capacity. We need to know what the rated maximum output of the system is. And oftentimes that's defined by identifying what the inverter is and how the modules are connected to that inverter. Then as we're beginning to find out more and more through our work, the surroundings or the environmental conditions in each of these systems is becoming really important, and oftentimes, again, not captured to quite the same standard. And that includes things like the solar obstruction. So what is the azimuthal obstruction stepping through east to west? Oftentimes that's captured as a monthly solar resource. So there are established ways that that developers at the residential and commercial level report back their energy forecast over a 20-year period, and sometimes that azimuthal obstruction is changed into a monthly solar resource. So now we've defined what our PV specification is. What is it? What sort of data do we need about the PV systems? This is how we go through and then simulate. We start again with that PV specification that I just described. We combine it with the irradiance. So we want to know what the irradiance conditions are at the global horizontal level, the direct beam, and the diffuse light. We'll also incorporate things like wind speed and temperature, relative humidity, and precipitation, all of which can have an impact on the irradiance to power model, which we use to then convert the environmental conditions into a power or energy output of a system. So that goes through and again, takes the PV specification. That tilt and azimuth is very important to being able to predict what the transposition to plane of array is. We then look at the equipment specification, see what the module performance would be under different light conditions, inverter efficiency and conversion to AC power, AC energy, and then what the reduction from shading conditions are. Depending on the utility use case, and we'll go back to that table and go through it in a bit more detail, but depending on the use case, we may want to aggregate the output of all the PV systems. We might have 100 systems on a feeder, or we may want the individual output of a single commercial building. Why is this important? We've looked at doing this a number of different ways, meaning we understand that we don't have perfect information about every single BTM system that's out there, and that's just going to be the case going forward. So what is the reason why we try to do this at a certain level of specification versus making some simplifications? One reason is the variation in power output throughout the day that you would see. Now, you're probably not going to see a lot of tracking systems on residential rooftops, but the diurnal profile or day-to-night power output of the rooftop system is going to vary depending on which way it's facing. And based on how a fleet of PV systems is made up, the diversity of the installed base is going to drastically impact how the aggregate output of the systems behave. We were asked this question by the ISO in California, and we've come up with some results through a CEC project that we worked on, where there's about 500 systems that have revenue grade meters provided by Itron, and what we did was we compared the output, and so the question became, well, what if you tried, what's the value in doing it through the approach of system spec plus environmental condition PV simulation versus just aggregating the output on the meter systems. And what we saw is that the application of the forecast model and the simulation model matched up pretty well to systems. We broke the system. There are 500 systems. We broke them into what we called good systems, meaning we had in the information management system, the central power clerk database, we had all of the specifications down to the shading. So we had a spec that defined what we believed to be a complete description of what was on site. That was a good system. Here we see a pretty good accuracy when it came to predicting the annual energy at the monthly level. And then when we added all systems, it actually didn't impact it that dramatically, meaning now we took, of those 500, all the systems that had a PV specification, complete or incomplete. It could just have the tilt and azimuth, or it might just have the capacity of the site. And when we summed up the accuracy numbers when looking at all systems and good systems, at an energy level, the accuracy is pretty good. So when it comes to the decision of trying to aggregate meters across a large fleet of PV, especially in some states where you're reaching hundreds of thousands of behind-the-meter PV systems, versus taking the approach of capturing the PV specification and then predicting through the environmental conditions, we think that that's a much more cost-effective approach. So now let's go back and talk about how does the solar forecast apply to these use cases. This diagram we'll take a minute here and talk a little bit more in detail. Going left to right really on the x-axis, we've got different systems on the utility grid. There's the sub-circuit, the feeder, up to the substation, and then balancing area-wide. Excuse me. Then going from top to bottom, or on the y-axis, we've got different processes associated with different time domains. So we've got a planning aspect. How do we build our grid for the next year, 2 years, 5 years, 10 years? Next month, do we need to make upgrades for new interconnection? As well as processes on the forecast side. So we want to know what's happening on the grid right now with regard to behind-the-meter PV, hourly, and then day ahead. And when we look at applying the different meteorological forecast models for solar irradiance, we further break this up into a grouping and data resolution. So we've got about 4 degrees of specification when it comes to the use case and the application of solar forecasting. We've got aggregate grouping, meaning do I take the total capacity and try to predict the total capacity of all of the behind-the-meter systems, knowing that that total capacity is made up of 200 individual homes, or do I want to know the individual output? And again, the data resolution is also important. So it could be sub-hourly, that could be down to the minute, or in some cases, we've had use cases ask for sub-minute data, or are we comfortable with hourly level resolution? And that can go either on the planning side or the forecast side. So as an application of solar forecast, we see the value in creating a platform that allows you to generate forecasts at these 3 different temporal and spatial grids. So you can start with a really wide area, 10-kilometer average irradiance over that entire area at an hourly level. We can step down now to a 1-kilometer grid cell and use half-hour data. And then there are use cases now that we're being asked for minute data. We want to know what the PV is doing on a minute level, because as you can see, there's quite a bit of variability that can be created sub-hourly. So when we went and designed the system to address some of these use cases, we wanted to look across what tools were available to us, and so what forecasting techniques really, what forecasting models do we have at our disposal to be able to come up with a system that can do what the use case is asking. So let's start by talking about the different forecasting techniques as a function of space and time. So the very short time scale and very focused area technique might use persistence. That might be within the next few minutes. You could take the output of the pyranometer here or the output of the PV plan and then persist it forward. You could also use Sky Imager, so this would be something that you would install on site, and it would look at the clouds, and it would give you a little bit more aspect ratio in the view angle of the Sky Imager, and you can tell there's clouds moving in or moving away, and that'll allow you to predict the irradiance or potentially the power output of the plant. At a wider scale, the satellite approach, it uses geostationary satellite imagery and uses a cloud motion vector approach, so it's vecting clouds based on their movement within the last 2 timestamps. And then farther out in time, and oftentimes at larger scales, though you can run nested or mesoscale grids, are numerical weather prediction models. On top of all that, you can apply statistical models. There's quite a, as far as the literature goes, there's quite a heavy weight in terms of the number of papers being submitted that focus on machine learning and neural net when it comes to solar forecasting these days. So now here's the survey of all the forecasting tools at our disposal. How do we take all of these and ones that we think are going to be most beneficial to behind-the-meter solar and create a single platform, a single output at those 3 different spatial and temporal resolutions? So what we did, and this is a project that we did with the Sunshot Sunrise program, where we looked at the benefit of all of those different models, again, starting with persistence, and then weighting them to the point where we're getting a maximum benefit on a single combined forecast model. So for the sake of time, I'll throw them all on here, and you can, if you want to go back and look in more detail what we found. The error statistics that we are reporting here are based on 7 sites. So this is a Radiance Prediction at 7 sites across the continental US. This is focused on creating an optimized continental model. When we take and then blend intelligently the different impacts of each of the forecasts, we can produce an overall forecast that beats any of the individual pieces. And as far as excuse me, application of forecast meteorology science to energy, this is the approach that we took. So last, let's talk about 3 different projects that we worked on in applying some of what we learned in those forecast comparisons to different use cases through the utility. So the first one is for load forecasting. So again, we start with these first 2 degrees. At the system level, we're looking balancing area wide. And most commonly, we're looking day ahead, but we're also looking hourly or in the real-time market as well. And now when we add both the grouping and data resolution, we want potentially sub-hourly on the day of, but really hourly for day ahead energy predictions for the scheduling market. And then we want to aggregate the output of the BTM PV systems. The problem, again, just to illustrate the duct chart example, is that load forecast models without an explicit input of the behind-the-meter PV are struggling because PV output is weakly correlated to the traditional inputs like temperature. And so here we're putting next to each other 2 different climate days. You've got a warm and cloudy day next to a cool and sunny day, just to illustrate the example of how these types of adjacent weather conditions can throw off a load model. So our actual load in green is better served by the orange curve than the blue curve. And we've been testing this now at the ISO level with our work in California for, I'd say, close to about 4 years. And what we're really seeing is a directly attributable benefit from the behind-the-meter forecast to the overall accuracy of the load model. And we're estimating about 20% improvement through the midday. This work's ongoing. We have more projects to figure out how we can improve that further, focusing on early morning load variability and other impacts that the behind-the-meter PV can have on the load model. The next use case, now we're starting to get down into more of the distribution grid. This is substation down. We're looking at the interconnection case and hosting capacity. Interconnection is the request of an applicant to add a new system to the grid on their rooftop or their commercial building. Hosting capacity maybe start to blend into more of the long-term planning, but it's an understanding of what a particular feeder or portion of the distribution grid can handle by the way of total behind-the-meter PV. So now we look at data resolution and grouping. Now we need to apply a sub-hourly prediction, though we're starting mostly at the hourly level, 8760 analysis for an interconnection hosting capacity study. And then aggregate, so what's the total impact of PV on that portion of the grid. This is a project that we worked on with PEPCO, where they are looking at understanding hosting capacity by using forecast of BTM PV. Now, this is forecast from a planning perspective, so it may use a look at the characteristic climatology as a way to predict the power and energy contribution of these BTM systems. And having the ability to do that allows you to walk through an increasing penetration here and conduct this hosting capacity study where we increase the penetration of the behind-the-meter PV and run scenarios where the grid model looks at number of voltage violations that would occur due to the increasing penetration. This is all relative to load. And as you do that, you can see that there's a certain point where there are no longer interconnections allowable beyond a certain capacity, and that might trigger an upgrade. So what PEPCO is able to do is they identify on all their feeders at what point do we need to go and invest more in the grid to support additional interconnections. The last one I'll talk about is a project that we're working on right now, and so we're in just completing the first year. It's I would call it best described as a DERMS project, or distributed energy resource management system type application. And for this type, we're looking at data resolution of sub-hourly and hourly, both in aggregate and in individual, though the individual is the main focus of this project. The project's being run by EPRI, and what their objective is to demonstrate within a single integrated DER. Now, this definition kind of has a flexible boundary layer here. This could be a couple commercial buildings, or it could be a single commercial building, and it could be a bundle of different technologies. So there's storage, different amounts of storage, different amounts of PV, potentially controllable loads. Here we show a heat pump, but one of the project sites, there's pool pumps as well. So controllable loads, and their objective is to demonstrate how this integrated DER, with the input of a solar forecast for the BTM PV, can execute a strategy that reduces the exposure of the electric grid to some of the variability that the PV might cause, while also optimizing the behavior of the hardware bundle in the integrated DER to extend the lifetime to as long as possible. So what does that mean? Let me describe that in a little bit more detail. So storage, batteries especially, so lithium-ion or any sort of battery storage, it's very good at responding very quickly to changes in the PV output. And on a day that we would say it has low variability, so showing down here a clear day, the battery and the integrated DER may not have to stress the equipment all that much. A cloudy day or an overcast day, same thing. The variability is a little bit greater. You might get some short-term cloud movement, things like that. But overall, you're not seeing large swings in the capacity coming out of the PV system. Now, depending on your location and your climate, you're going to see different scenarios where the variability across the day gets a lot more varied. So you could have relatively clear to an overcast afternoon, moderate variability to where the equipment on its own is able to manage that variability, but still starting to undergo some additional cycling, right? It's beginning to be used more, and so the cost of that equipment over its lifetime is going to increase to the point where, yeah, I mean, there's maybe a few days in the year, maybe only one day in the year, but that type of high variability day could reduce the lifetime of your equipment quite considerably. So the goal of this project is to demonstrate then how, if we are able to predict this variability, can the controller, the local controller here, operate the integrated DER such that it optimizes how the equipment is being used and also the draw from the electric grid, the reliance of the commercial customer on the electric grid. Some of the work that we're doing under this project focuses on advancing the solar forecasting technology. That's through satellite, the cloud motion vector model. That lends itself very well to BTM prediction because the resolution of the GOES satellites, even before the launch of GOES-R or GOES-16, was down to about 1 kilometer grid. And so having access now to these new satellites allows us to test whether our existing forecast models applied to a faster refresh rate, higher resolution, could either allow us to increase resolution below 1 minute or come up with a better 1 minute forecast prediction. Again, all for the goal of extending the lifetime of the DER hardware and reducing the variability that the distribution grid would see. So that covers my talk for today. Thank you again to the UBIG group for inviting me to speak. I will open it, by questions, and feel free to connect by email or through LinkedIn.
Okay. Thank you, Skip. I see only one question in the queue right now, and I'll have to defer to Margaret. It's basically, will the slides and or recording be available somewhere from UVic?
Yes, we're planning to send a follow-up email after the end of this. It'll probably be tomorrow when it goes out, so be on the lookout for that.
Okay.
And then I have a question. Skip, we may have to go back into some slides to answer this, but Mark asked, I believe it was during the utility scale forecast value example. It was a chart that has about 5 years worth of data on it and 2 plots. It's like an output and a number of units. And he asked, was this, let me find it. And he asked, why do the counts appear to be declining over time?
Why do the counts, let me just make sure I get to the right slide here.
Right.
So, we're looking at, so at the utility scale forecast, why are the counts declining over time? I'm not sure I have the right slide here.
It was the one with good systems, I believe.
Oh, okay. Gotcha. Okay.
Yeah.
Yeah.
Okay. So the number of of systems that reported across this time scale here, starting in 2011 through the end of 2015. The reporting on those systems was varied. So the most systems were reporting in 2011, and I think there was a large data gap here that we removed in, what is this, the November of 2013. So that's kind of an anomaly there. But the number of systems that were actually reporting from the meters was declining over time. And so we weeded out any systems that were not giving us real power data. We didn't want to include those in the comparison because they weren't reflective of what was actually happening in those systems at that time.
Okay, another question was, why is it important to worry about variability at the local level discussed a short time back?
Sure, so let me go to this slide, maybe sorry to skip around here. There's a better way I can jump between slides, but either way. So the variability at the local level, I think, starts at the building. Described in this example is the usage of that hardware bundle in the integrated DER to reduce the impact of that variability. Now at the transmission level, there isn't as much of a concern. It's the same thing. The transmission level, the ISO doesn't care when an individual building turns their lights on and off. But depending on what's installed at the distribution level, if you're trying to optimize the behavior of the DER, you want to understand and be able to forecast the variability. And then as it goes, actually this relates to kind of a couple cases here, the interconnection or hosting capacity. There's requirements on what level of voltage must be maintained on the distribution grid. And variability at a small level, even if it's spread across a feeder, which depending on where you are in the country, what utility you're at, and what feeder you're on. So it's different for every feeder in the country. But depending on what the configuration of that feeder is, it may or may not be able to weather that variability when it comes to regulating the voltage. And so that's why we're starting to care about it. I wouldn't say it's traditionally been something that has been looked at, but in the last few years, we've been certainly asked for our ability to forecast at that level.
Okay. Do you see this technology as a means of moving more PV into the Midwest and other regions with weather pattern variation?
Yeah, so the question is does solar forecasting and specifically BTM solar forecasting enable higher penetration or more integration of PV subject to what the weather conditions are? And I'd say absolutely. There's a lot of great work that's going on in HECO, which I often think of as the extreme example of solar variability. Not only are they a completely isolated grid, but they have this is Hawaii Electric Company. They have a really high penetration of PV, and their cloud patterns are actually really challenging in a lot of ways. They get these cloud formations that come off of the ocean and form due to the topography of the islands, and it can create some really, really small clouds and really, really fast forming clouds. So if Hawaii can do it, I would say that anywhere in the continental U.S. and as far as my meteorology understanding goes, I would think that anywhere in the U.S. can do it.
This is actually a follow-up question to the question about the local levels.
Mm-hmm.
Let me scroll back to, and she wants to know if the voltage is controlled, then should this not be a problem?
Yes, yeah. So maintaining the voltage on the line is as I understand it, a regulated exercise. They need to maintain certain voltage on the line, and that can be done through a number of hardware solutions. Similarly, in that DER example, so if we go to to this example. Similarly, you could operate without a solar forecast here, or without a more planning level solar prediction. But the risk you run is increasing the cost of the hardware bundle. So can you do this reliably enough where really what you're trying to, the way I think about it, what we're trying to do is shift more of the workload from the storage. So instead of just defaulting to using the battery, to being able to use the controllable loads as a demand response type event. So it's a localized demand response, not the same as a utility might issue a DR signal. But at a local level, if you can reduce that variability or ride through some of the PV variability with a combination of the smart inverter and the controllable load, then maybe you can extend the lifetime of your battery, which right now is the most expensive part per number of hours used, a piece of that DER bundle. It's an expensive way to manage the variability. So similarly, in terms of voltage regulation, if you can better plan and better design the grid, this is on a longer time scale, so potentially a few months to year, to 5 years, 10 years, if you can better predict the impact of the PV, you might reduce the reliance on the hardware and thus depreciation of that equipment.
The last question I have right now is, what role do you see for Energy Plus buildings in DC grids, microgrids, excuse me?
I don't. That's a question that I have to admit I don't know if I have enough exposure to be able to answer that. If either the author or Bob or Margaret, so Solar Plus Home, would that be something equivalent to what I described as that integrated, or the DER, integrated DER? So they mean a solar home with storage, a smart thermostat or controllable load, and potentially even an EV as a battery on site. Is that your guys' interpretation too?
Well, that's potentially a tiny microgrid with some different control, but the DC is another issue, especially in residential environment, because that's mass market, and all the equipment is built around AC right now. In buildings, I guess there's been discussion of that, and that requires a sort of a wholesale change out of all the pieces and parts, in terms of breakers, protective equipment, and all that. But it's a topic that's gaining a lot of traction, even in the IEEE PES, Power and Energy Society. I just don't know if anybody's really doing it yet, even a large-scale demo.
Okay, I've got a few more in. What is the data/communication requirement for CAISO to set up the solar forecast for the whole California region?
What is the, let me make sure I understand this question. What is the data requirement to set up the forecast for the entire California region?
Mm-hmm.
I think this question is getting at what different data fields, resolutions, and groupings are required for the CAISO BTM forecast. And so I'll go back to this case, which is the load forecasting case, and this can apply to any transmission area, not just the CAISO, but and it will certainly vary again. Different grids operate in different market structures. But what we've seen is that the forecast data aggregated to the transmission scale, so we take, again, as much of the individual BTM system specifications run through our solar model with our solar radiance forecast, aggregated to the transmission level, so aggregating all that capacity from individual predictions, and then provided at a day ahead basis for the scheduling, as well as a 5-15 hour ahead level for the real-time market. And the grids that are defined by the ISO are based on their geographic regions, but because we have a certain amount of data, and again, not all of the PV systems that are going into our prediction are fully enumerated by the way of modules, inverters, tilt-azimuth, shading. But because we have a significant portion of that, the aggregation can be fairly arbitrary. That's another good thing to point out, is that starting with that data management system in the middle allows you to address a lot of existing use cases and existing applications, but potentially also future ones if you start from the bottom up and then aggregate. Because you could change the designation and we'd be able to, it would change the BTM contribution based on aggregated output, and we could do it reliably based on the available weather. So hopefully that gets to the question. The forecasts for day ahead do go in out to 7 days as well, so there's a longer term forecast horizon, but as far as I understand their market, there's a day ahead and an RT-PD, or real-time pre-dispatch.
Okay. Do you have any recommendations as to what level of DER penetration justifies what level of expenditures on BTM PV forecasting? That was probably a lot.
I think I know where this question is going, because it's certainly I would say one of the most important points to think about, because it gets down to the value discussion. At what level do we need this? I can speak from the experience that we're being asked for this level of detail, either through demonstration projects or through commercial implementations. The utilities that ones that we work with are asking for this level of information. That value assessment, I can't give a kind of a threshold by any means. I think it again depends on the grid. There's every utility has their own feeder network. There's unique feeder. Sorry, I kind of compounded those. There's a network system like ones in some of the higher densely populated areas, and then there's more of like the spoke and hub where you've got feeders that run out from a single point and run out to the end of the feeder. And predicting the impacts on those is different. The loads on each feeder is different as well. So I certainly have not seen, nor could I predict what a reasonable threshold would be, and it will vary based on the feeder configuration, and every feeder is different.
And we have one that would like to see if you could comment on what will happen as BTM installed PV increases substantially in size. Do you have any?
Yeah. So this is, I think, getting at the point that some of this is maybe more driven through the installers or the EPCs, where they're either the shift or the balance of commercial industrial to residential is increasing, or even the residential systems are getting bigger, I mean, even incrementally due to some improvements in the modules. So you can put more or higher rated individual panels on your roof under the same area. You can get a more DC nameplate on your roof. I don't know if I have a good answer for that on what will happen. Yeah, sorry.
Okay, this is the last question, I believe. Have you looked at applications to solar and storage with enough predictability to reduce peak demand charges reliability for individual commercial systems?
Yeah, so that's, I think, taking the view of, this question takes the view of the commercial building as the entity that we're trying to optimize for. So the demand charge, just for the benefit of any other attendees that might not know what they're referring to, demand charge is a charge that the utility applies through the tariff structure that focuses on typically a maximum use, a power draw over a 15-minute period. This is, I think of it as a one and done through your billing period. So if you're in monthly billing cycles and you've got one period, you could use no energy or very low energy for the entire month, but at one 15-minute period, you turn on all your equipment and you spike your usage, you will get charged a demand charge in a commercial, typically a commercial rate structure. The goal of reducing that can be done by optimally dispatching storage. PV itself doesn't always align with the demand charge, so PV may reduce will certainly reduce their energy charge as long as the PV is working, but may not reduce their demand charge. And so I can see this is a slightly different project again that we're working on, where we're trying to forecast. This is not the EPRI project, but we're trying to forecast at a 15-minute level what the solar is going to output for the direct goal of reducing the demand charge. So using the load to shift, but using that economic factor to really drive the control strategy. So I think from what I've seen, I think the back of the envelope we've seen is between about 6 and 10% reduction in the electric bill. Now that also takes into account that there's a lot of load variability, so you have to be able to predict the load of the commercial building, which is oftentimes a lot more difficult because again, you can use neural nets to train a load prediction, but the individual behavior of that commercial building can drastically outweigh the ability of that load model to predict an individual building's performance. So just as an example from that project, we demonstrated this at a community college that had a 100 kilowatt system and roughly a 200 kilowatt peak load. So they were sized at about 50% of their peak load, and the load prediction was doing a great job. Normal week, the students would come in and the usage would be fairly consistent, and then one day that wasn't predicted. They had a huge assembly in their assembly hall, and that killed the demand charge for that month because again it's a one and done. So I think there's a lot of promise to be able to do that, especially if you now start to incorporate the right size of storage, optimally dispatching the storage. I think there can be a lot of benefit economically to the commercial building owner, but I haven't seen something that's foolproof just yet.
Well, I think that's all the questions that I see come in.
Great. Well, that was great questions from the attendees. Thank you.
Very good. Very good.
Thank you for that great discussion.
Okay. Without any further questions, we can all get on to our normal stuff. Thanks again. Thanks from Charlie for attending. Thanks to Margaret for logistics and the arrangements. And I guess we'll see you next time, or hear you next time.
Thank you very much, Bob.
All right.
Thanks, Margaret. Thanks, everybody.
Bye-bye.
Bye.